Hello everyone, welcome to another presentation from Jinko Electronics. Today we have an exciting presentation on maximum power transfer theorem for DC circuits. Consider the following circuit. We have a power source V1 12 volts, internal resistance Rs 10 ohms and load resistance RL 100 ohms. We need to investigate how can we deliver maximum power to RL so that we can maximize our source. In a communication system, the radiation resistance of an antenna must match the output resistance of the radio transmitter. Another area of application is in designing of amplifier circuits. For instance, a class A amplifier needs the output impedance to match the load resistance for maximum power delivery. The maximum power transfer theorem can be stated as the power transfer from a supply source to a load is at its maximum when the load resistance is equal to the internal resistance of the source, which is when RL is equal to RS. We have our measurement setup. We have 2 watt meters and 2 volt meters. Watt meter XWM1 measures the power dissipation in the battery, while the other meter, watt meter by my right, measures the power dissipation in the load. Then we have 2 volt meters, one on top. The one on top measures the voltage drop across the internal resistance, and the one by my right below, bottom right, measures the voltage across the load resistor or load resistance. Here we are in the multi-sim environment now, so I'm going to be drawing the circuit from scratch so that you can follow along. Okay, we move to the component toolbar. We click on the sources. We need a DC power. Select this, place on the workspace. Then we move to basic group. We look for resistor. It does pick anyone. We'll set the values later. Then we look for ground under sources. We take for ground. You can place anywhere here. I think that's all we need. We move to in use list to pick another resistor there. We rotate by pressing Ctrl R. Then we begin to draw. Just click and draw. Click and draw. Our circuit is complete now. So we change this value. We call it, when we double click, we go to label, we call it RS. And we change this to RL. Yes. Then the value here is too high. We move to value, change it to 10 ohms. So this other one, I can change it to 1 or 100K. Now I want to vary this RL. So I have to match it with this one. So then what I have to do, I'll click on view. I'll create a parameter or a placeholder for RL so that I can vary it. So under this is already even set to 1. But let me delete this. We just click here, you press R, you type RL. You can put any value you like. I put 1 here. Doesn't really matter because we are going to vary it. Now, my measurement setup, I prefer using this in probes than using this meter. So I will check for, I need for voltage, 2 voltmeter. So I'll click on the voltage and click here. 2, this is for volts. Then I need for watts. Okay, for volts, it's not here, sorry. It should be placed across the node. Yes. That's this one now is for RL. So let me name it differently. Let me put V RL so that we'll know it. Yes. Then for this now, it should be from node 1 to node 2. So I need a differential voltage, which is this. I click, I move to the place I want to measure. This is it. Then as I click, you see another probe comes out, which is the reference. I take this as my reference. So I'll now say I'll change it to VRS. I think we are complete for now. Let me just run it and see how it's going to read. Should be interactive simulation. Good. Yes. Yes. But I don't want all these readings. I just need voltage here and voltage here. So I'm going to customize it. When I double click, I move to parameters. I move on custom. I disable all of them. I just select voltage DC. That's all I need. I do the same here. Custom. Disable it. Click on no. It should be no. Yes. Enable it. So I only need those 2 parameters. Next, I need my watt meter. Watt meter should be placed on top of the component, not at a node. So when I click this one, this one too should be placed across. I set my dashboard here. So if I run it now, you can see how many watts. This is in nanowatts. This is in milliwatts. You see, they are not matched. Alright, we are ready to run our analysis now. We are going to be doing a parameter sweep across RL. That will be alternating the value of RL and see how the power will be affected. Now we'll move to parameter sweep. We click. Under the parameter sweep dialog box, we have sweep circuit parameter. It is RL that we want to vary, and we know it's 1 ohm according to as we set it before. And the sweep variation is decade. And the start and stop, it will start at 1 ohm, stop at 10K, and for each decade it will run to give a value of 10 points. Then under more options, we have DC operating point. We will not do any of this because this is the one we want, DC operating point. Then we'll move to the output, what we want to plot. First, we are going to plot the power of the two resistors across RL. Let's see how it's going to be. We are going to remove this one first. So power across the load is this one. Power across the battery is this. We are going to run the sweep now. Fantastic. The green trace is the power across the battery, where the blue trace is the power across the resistive load or load resistance. They now meet at their maximum point. They meet at 10 ohm. That is when the resistance, the RL, is 10 ohms. That is their maximum. So if we trace it with our cursor, for it to be, you see it's 10 here. For us to get it right, I'm going to type 10 so that it will be exactly at 10. You can see it's exactly at 10. And exactly at 10 is giving us the maximum power is 3.6 watts. That is for one plot. The next plot we are going to do, we are going to plot the drops. The next plot we are going to do the battery. We are going to plot across the resistors, the resistive load, and see. So we are moving back to the parameter sweep option dialog. We are changing it. We are not plotting for power again. Remove these ones. We are plotting for the voltage across the battery and the voltage across the resistor. You click on run. You can see at 10 again. This 10 is constant. At 10, we are going to set it at 10. Very good. The voltage drop across each one is 6 volts. You can see at this 10 is 6 volts. So at maximum power delivery, each resistor must have the same voltage drop. That's another thing. Once they have the same voltage drop, then that's the maximum power, because they will share the power into two equally. Then the last one is very important, efficiency. We are going to see that at maximum power, what is the value of the efficiency? Is it up to 100%? Is it up to 50%? Let's try it. For this one now, we are going to, I'm going to remove these ones. We are going to add the expression. And I've saved the expression. I'm coming. Add the expression. We are going to copy it. You can see. So it's very simple. The output power divided by the total power times 100. That is the efficiency. Wow. You can see. So let's check at 10 again. At 10, you can see the efficiency is 50%. As the resistance of RL increases, the efficiency also increases. So at maximum power, we are getting 50%. All these plots, we can gather all the data, all the graph values, export it to Excel, and continue the analysis if we like. But we have seen from our analysis, let me go over it again. This one is for the power of the resistors. We can see that maximum power is at 10 ohms of the resistive load, and at that maximum power we are getting 3.6 watts each. Okay, then at maximum power the voltage drops are usually the same. The total source is 12 volts, so each one will have 6 volts each. Okay, then at maximum power the efficiency is 50%. So that is how we are wrapping up for today. Thank you very much for watching, and please subscribe for more interesting videos.